Hello everyone, I am Professor Anish Vora. In today's video lecture, we will study about no-load characteristic of three-phase induction motor. In case of no-load characteristic, we have to calculate no-load current. And to calculate no-load current, we know that no-load current is composed of two components. One is magnetizing current. Magnetizing current component is required to generate flux or magnetic field. Another component, that is a loss component, and loss component is required to fulfill the loss during no load condition. So if we see the phasor diagram, so on the x-axis we take as a flux axis or current axis. On the y-axis, we take a voltage axis. There is a 90-degree lagging between voltage and current or flux. Along the flux axis, we have current component, and that is known as magnetizing component, which is lagging by 90 degree to the voltage axis. In phase with the voltage, we have loss component, and based on these two components we have our no load current. So this is our no load current. So from the phasor diagram we can say that no load current component, that is composed of magnetizing current as well as loss component. So magnetizing current. Now in case of magnetizing current, in case of induction motor, the magnetic circuit is composed of different components. That is a air gap, then stator teeth, then we have a rotor teeth, then stator core and the rotor core. So before we start calculating magnetomotive force for all individual part, let us study about magnetomotive force. The value of magnetizing current can be calculated by assuming the sinusoidal distribution of flux and magnetomotive force in the magnetic circuit of the induction motor. The permeability of the magnetic material of induction motor varies in stator and rotor teeth. The sinusoidal magnetomotive force produce flat topper flux density distribution curve. The assumption of mean value of magnetomotive force will give larger value of the flux and comparatively smaller value of the magnetizing current. The true value, however, the maximum value of magnetomotive force will give smaller flux value and large magnetizing current. So because of this, some intermediate position is selected which usually correspond to flux tube crossing the air gap at 60 degree from the interpolar axis. This is because a flat wave can be approximated to a sine wave by superimposing on its third harmonic wave. So in all our calculation, the value of flux density at 60 degree is will be considered. So we start with the magnetomotive force for the air gap. So as we discussed, flux density at 60 degree from the interpolar axis will be considered. So B and suffix G is for gap at 60 degree, that is 1.36 times average flux density. Magnetomotive force for the air gap, from the flux density we can able to calculate magnetomotive force. So magnetomotive force for the air gap, that is ampere turn for gap, G is for gap, that can be calculated based on the flux density at 60 degree we have calculated. So ampere turn for the gap, that is 8 multiplied by 10 raised to 5 multiplied by flux density at 60 degree multiplied by kg and multiplied by lg, where kg, that is a gap contraction factor, and lg, that is air gap length. So this way magnetomotive force for the air gap can be calculated. Now next, that is magnetomotive force for the stator teeth. Magnetomotive force for teeth is found out by finding flux density at section 1/3 height of the teeth from the narrow end. In case of tapered teeth, we know that flux density is not uniform along the whole section of the teeth. So we have to consider at 1/3 height from the narrow end. So let us see. So now this is a slot. This is tooth. We are just calculating stator tooth flux density, and from this we will derive magnetomotive force required for the stator teeth. So this is the width of the stator. From the narrow end we take two different heights. One is at 2/3 condition and one that is at 1/3 condition. So from this diagram, it is clearly or easily we will be able to calculate flux density at 1/3 height from the narrow end. And to calculate flux density, we actually require width of the rotor teeth from the 1/3 height from the narrow end. So let us see flux density at 1/3 height of the teeth from narrow end. So that is a flux density B suffix Ts, that is for teeth and stator at 1/3 height, and that is given by this equation, that is flux 5m divided by slots per pole multiplied by net iron length and multiplied by width of the teeth at stator at 1/3 height. So WTS at 1/3, that is width of the tooth at 1/3 height from the narrow end. To calculate the width of the stator teeth, we use this equation. So we have actually slot pitch, that is a pi multiplied by d. D is the diameter, plus 2/3 DSS, that is the depth of the stator slot divided by number of slots, and minus WSS, that is width of the slot. So from this equation we will be able to calculate width of the stator teeth, and if width of the stator teeth is available, we can easily able to calculate flux density of the stator teeth at 1/3 height. So calculation of magnetomotive force for stator teeth is also based upon flux density of stator teeth at 60 degree. So flux density of stator teeth at 60 degree, that is 1.36 times flux density of stator teeth at 1/3 height. At 1/3 height we will be considering as average flux density. So magnetomotive force for the stator teeth, that is ampere turn for stator teeth, can be calculated based on the flux density of stator teeth at 60 degree achieved. from the BH curve, we can easily calculate ampere turns per meter, that is small at ts, and multiplied by length. In our case, it is depth of the stator slot. So from this equation, we can easily able to calculate magnetomotive force for the stator teeth, where AT, that is stator teeth AT, can be obtained from BH curve corresponding to flux density of stator teeth at 60 degree. So after magnetomotive force calculation for stator teeth, our next task, that is to calculate magnetomotive force for the rotor teeth. So magnetomotive force for teeth is found out by finding flux density at section 1/3 height of teeth from narrow end. So this is our rotor. At outer periphery we have slots and teeth. Let us see how to calculate width of the rotor teeth. So this is a rotor diameter. We have stator diameter minus we have air gap. So we get the rotor diameter. From the narrow end at 1/3 height, we have our slot depth. From the 2/3 height, so our slot is divided, or teeth rather, is divided in two parts. One is 1/3 and one is 2/3. This is known as the depth of the rotor slot. Same way on the upper side. On both the sides this is same. So this is 1/3. Same way we have 2/3. So mean diameter at 1/3 height from the narrow end, that can be calculated as a total rotor diameter minus 2 times on the upper side as well as on the bottom side. 2/3 of the depth of the rotor slot. So we get a mean diameter at 1/3 height from the narrow end. So this diagram is very important. From this diagram we can easily able to calculate the required dimensions. So let us now calculate magnetomotive force for rotor teeth. Flux density at 1/3 height of the teeth from narrow end. So flux density, again TR, that is the rotor teeth at 1/3 height, is given by this equation: flux divided by slots per pole multiplied by net iron length and multiplied by width of the rotor teeth at 1/3 height. In each calculation, this width is very important. So width of the tooth at 1/3 height from the narrow end, and then that can be calculated from this equation. Basically this equation is pi d divided by rotor slots and minus width of the rotor slot. So calculation of diameter, we take d minus 2/3 of depth of the rotor slot. As we have seen in previous diagram, we can easily able to calculate width of the rotor teeth. Once we have flux density available, then calculation of magnetomotive force is also based upon flux density of rotor teeth at 60 degree. So flux density of rotor at 60 degree is 1.36 times flux density at 1/3. So flux density of rotor teeth can be easily calculated based on ampere turns of the rotor teeth multiplied by depth of the rotor slots, where ampere turn for rotor teeth can be obtained from the BH curve corresponding to flux density of rotor teeth at 60 degree. So next step, that is to calculate magnetomotive force for stator core. Magnetomotive force per meter ampere turn for stator core, C is for core and S is for stator, corresponding to flux density is found from BH curve. So let us see the diagram for stator core. We have bore diameter, then we have depth of the stator core, and then we have depth of the stator slot. So from this diagram we will able to calculate magnetomotive force for the stator core. Length of the path through the core can be taken as a 1/3 pole pitch at the mean core diameter. So length of the path through stator core is important. How to calculate? So length of the stator core, that is a 1/3 of the pole pitch. So pi d divided by pole. So mean diameter here we consider d plus 2 times dss, that is depth of the stator slot, plus dcs, that is depth of the stator core. And therefore magnetomotive force for the stator core, that is ampere turn for stator core, that is ATCS multiplied by length as we have calculated. So this way magnetomotive force for the stator core can be calculated, and same way magnetomotive force for the rotor core can also be calculated. Magnetomotive force per meter ampere turn for the rotor core corresponding to flux density is found from BH curve. Let us see the rotor dimension. We have rotor diameter. We approximately considered as a bore diameter because air gap length is comparatively negligibly small. Then we have slot depth, rotor slot depth, and we have depth of the rotor core. So from this diagram it will be easily able to calculate magnetomotive force for the rotor core. Length of the path through the rotor core, that is LCR, that is rotor core. Again it is at the 1/3 of the pole pitch, so pi d divided by p and 1/3. So to calculate d, we have main diameter minus. Here we take a minus. In stator we have plus. In here we have minus. Minus 2 times depth of the rotor slot, that is on the upper side as well as on the bottom side, minus dCr, that is a depth of the rotor core. So magnetomotive force for the rotor core, that is ampere turn rotor core CR is equal to ATCR multiplied by length. So now total magnetomotive force. So total magnetizing magnetomotive force per pole for flux density at 60 degree, that can be calculated as addition of all the individual magnetomotive force we have calculated. That is total magnetomotive force AT60, that is a addition of all the magnetomotive force, that is for the gap, for the stator teeth, for rotor teeth, for stator core, and for the rotor core. Based on total magnetomotive force, magnetizing current or phase can be easily calculated as 0.427 times P, that is number of pole. Total magnetomotive force at 60 degree we have calculated, and divided by kWs, that is a winding factor for stator, and Ts, that is stator turns per phase. So this way we are able to calculate magnetizing current component. Same way we have another component to calculate no load current. As we discussed earlier, we require two components. One is magnetizing component and another is a loss component. So loss component now depends on losses. So we have iron losses. Iron losses, in case of iron losses, we have hysteresis loss, we have eddy current loss, we have surface loss in the teeth due to variation of air gap flux density, we have tooth pulsation loss due to variation of teeth density, and losses due to non-uniform flux distribution. So we have total iron loss, but to calculate total iron loss, we consider total weight in kilogram, and we find from the graph specific iron loss, that is a watt per kg, and this way we will calculate total iron loss. Same way we have friction and windage loss, and that also depends on a rating of the machine, that is a standard, and from the standard table, based on the rating, we will able to calculate friction and windage loss component. And therefore total loss component of the current, that is a total no load loss divided by 3 times voltage per phase. So this way we will able to calculate loss component of the current. We have both the component now available, that is magnetizing component as well as loss component. Based on this both the component, we will easily able to calculate our no load current. We have discussed earlier at the initial stage that no load current is composed of magnetizing as well as a loss component. So this way no load current or no load characteristic of the 3-phase induction motor can be calculated. This characteristic is very important because one of the performance parameter, that is power factor, that is broadly depend on our magnetizing current component. So this way we able to calculate no load characteristic. Thank you very much. In next video lecture, we will discuss about leakage reactance and short circuit characteristic. Thank you for watching my video. Keep watching my video. Thank you very much.